Alright, so now we are going to solve some conservation of energy problems for those of you that struggled with that assignment. The first question says that there's a block. It's moving at 3 meters per second. How far will it compress that spring? So it starts with kinetic energy only. It ends with spring energy when it comes to rest. I'm calling that ES for spring energy. I just want to modify my this here because it's not accepted. So that just expands to 1/2 mv squared equals 1/2 kx squared. And you've got all those values here. Here's the speed, that's v, that's k, the spring constant, v, k, there's the mass. Anything else? No, that's everything we need. And we are just solving for x, which can be a little bit challenging algebraically, but that's part of what you have to do in these assignments is battle through that. Number 2 shows a ball being thrown vertically upward from the roof. So it's starting at position 1 and it's going up, and then it gets to a high point where it goes down and it lands on the ground probably at a faster speed than it started at. And part A says, what height does it rise to? So for part A, you're really just going, it starts with kinetic energy and some gravitational energy because it's got some height. So that's going to be a 1/2 mv squared and an mgh. And on the other side, when it gets to its maximum height, so let's call this initial kinetic energy, initial gravitational energy, then it's going to stop and it's just going to have gravitational energy. And you will be solving for the height in this side of the equation, mgh. These values over here you can just calculate. This one you're going to have to solve for. That one you're going to have to solve for and do a bit of algebra. It looks simple, but that's probably the hardest question in this situation. Because in part B it says what velocity does it hit the ground with? Well, you can just use that same calculation, EG initial plus EK initial. So you already have that number. It's on the left side of your equation for part A. And then you're just ending with kinetic energy, which is 1/2 mv squared. And you were solving for V. You'll have to take a square root at the end or something like that. I think if my memory serves me correctly, the maximum height's like 32 meters and the speed's somewhere in the 20s. So this shows a roller coaster, and it's going to end up at various points, A, B, C, D, E. It says it's at rest at point A. So at point A, it only has gravitational potential energy, no kinetic energy. After that point, it's always going to have some kinetic energy because it gets down here. Obviously, it's going to be moving. It also has some height, so it also has gravitational potential. When it goes up to C, it's going to slow down but not stop. And then it's going to go all the way down to D. So the first question says, what's its maximum speed? Well, it's going to have maximum speed or maximum kinetic energy whenever its height is at the lowest. So that is right here at point D. All right, so let's say it starts just with gravitational energy. That's at the top. That's at the 9.5 meters. And then it's going to get to point D still with some gravitational energy. Let's call this initial and this final. But now it's also got some kinetic energy. I think the speed there ends up being somewhere around, you know what, I can't remember. But you will be solving for the speed in this term right here. It's 1/2 mv squared, solve for V. You have all the other values. That's the setup for part A. Part B says, what speed does the roller coaster arrive at point E with? Well, it's a similar calculation. You're going to go EG initially, that's at point A, equals EG at point E. I'll even write a little E in there, plus the kinetic energy at point E. And again, you're just solving for V. So it's the same. It's the same calculation, except since you're at a different height, you're going to get a different speed. It's going to be a slower speed than the maximum speed there. And then part C asks you something kind of complicated. I actually used to have it on the grade 11 university prep test, same question. Some of you people will remember this. It says it's going to go that far and it's got to come to a stop after point E. To come to a stop, you have to get rid of the kinetic energy. You can get rid of kinetic energy by doing work to cancel out the kinetic energy. Work is equal to force times distance. Kinetic energy is equal to 1/2 mv mv squared. Use the speed that you calculated for point E, the mass of the roller coaster, and then divide by the distance, and you're going to get force equals whatever that kinetic energy is, 1/2 mv squared, divided by that distance, that 5 meters. And that'll give you your braking force required to stop that thing in just 5 meters. That's a tricky one. Hard to get that one on your own, but some of you did get it. This one's similar to the first one, except instead of something moving and then running into a spring and compressing it, this one you're holding it against the spring, letting it go, and it gets to some speed, and then it slides up a ramp. And saying how high does it, well, eventually it says how high does it get up the ramp. The first question is easy though, and it confuses some people because you've just done some difficult calculations, and this one's just simple. Find the elastic potential. What's the formula for elastic potential? We're calling that ES. It's 1/2 kx squared. And you have those values. You have those values. It tells you the stiffness of the spring somewhere. That's K. I'm just going to go up and look at it. It's 800 newtons per meter. So that's going to be 1/2 800, and how much are we compressing it? 0.22 meters. Don't forget to square that. I think it works out to around 19 or so joules, but let's check the calculation. The maximum velocity of the mass, that'll be right when it leaves the spring. That's when it'll be going fastest. So it'll start to slow down once it starts going up the ramp. So maximum velocity is going to be whatever energy you got here is all going to be converted into EK. So it's like the spring initial energy is going to all be converted into kinetic energy. So whatever number you got in the last calculation, like I said, I think it's around 19 joules, you go 1/2 mv squared and solve for V, and that'll get the job done for you. Then it wants us to do another calculation. It says find the height that it gets to up the slope. So that's a vertical height. So it's kind of the same calculation again. The initial spring energy, except now it's not being converted to kinetic energy. Now you're going to go all the way to gravitational potential energy, which is mgh. And you're just going to solve for h. Like I said, same energy you had from before is going to go into here, the 19 or so joules. Number 5. A Hooke's law spring is compressed 10 centimeters by an applied force of 50 newtons. The spring is then used to project a marble straight up into the air. How high does it rise? It looks complicated, but it's just like the calculation we just did. You've got some spring energy initially, and you're converting it all to get to a maximum height of gravitational potential energy. Expand these to different formulas, and you've got 10 centimeters, got to be in meters, 0.1. That's your X for in your spring. The applied force, this is F. So we have to do a little side calculation first. K is equal to F over X. That comes from Hooke's law. And that's going to be 50 divided by 0.1, which makes 500 newtons per meter. But then we're all right. The combination of those, and that's your K value for your spring formula. And then again, you're just solving for height in the gravitational term. Keep moving down. Number 6. Diver jumps 12 meters to hour, no initial velocity. What velocity does it hit the water with? All right. So no initial velocity, just gravitational, turning into kinetic energy. And you're solving for B. B says, what would the impact velocity be if in jumping from the tower he gave himself an initial velocity of 5 meters per second? That one's a little harder mathematically, because now you don't just have gravitational potential initially, you also have kinetic initially. But it's still all being converted into a final kinetic energy. So this is going to be mgh, initial height, that's that 12 meters I think it was, 1/2 mv squared, now it's that 5 meters per second that we're adding here. And we're going to set that equal to 1/2 mv squared, and we are solving for that v right there. We got one more. Let's try to extend the page here. A ball bearing of mass sitting on a vertical spring whose force constant is that. It's a little easier than the other spring question. By how much must the spring be compressed so that when it releases, the thing will go all the way to 3.1 meters? Did one very similar to this just a second ago. mg, we're trying to get it up to 3.1 meters, except now we're solving for how much do you have to compress the spring, right? 50 grams has got to be in kilograms, so that's 0.050 kilograms. Over here, it gives you the 120 for the spring constant, and you have to solve for x. Well, that sets up all of the problems. Whether or not you can actually apply some of that stuff and get them done will be up to you. Hopefully that helps, and if it doesn't, just come talk to me. We'll get it done.